Have you ever stopped to consider why wind turbines all share a strikingly similar design? It's a common sight, these towering structures with their three long, slender blades gracefully spinning. It's easy to assume it's simply for aesthetic appeal, but the truth is far more intricate and fascinating. The design is the result of overcoming significant physics challenges. At its core, it's about the science of kinetic energy harvesting, the art of capturing the wind's power. It's also about the relentless quest for the ultimate lift-to-drag ratio. To truly understand the shape and form of these turbines, we need to imagine shrinking down to a miniature size. We'll ride the wind itself as it approaches a utility-scale wind turbine. As we get closer to the blade, take note of its carefully crafted shape. It's not a simple, flat board. It's a high-precision airfoil geometry. This airfoil design is similar to the wing of an airplane, but optimized for a different purpose. As the wind flows over the curved surface, something special happens. A pressure differential is created, a subtle but powerful force. The air moving over the top surface accelerates, creating a low-pressure zone. This low-pressure zone acts like a gentle but persistent suction, pulling the blade forward. This is the essence of aerodynamic lift, the key to harnessing the wind's energy. But there's also a hidden enemy at play: drag. This is the friction of the air, the resistance that tries to hold the blade back. To maximize power generation from the wind, engineers employ a sophisticated technique. They use CFD analysis, or computational fluid dynamics. CFD analysis helps them find the perfect angle of attack for the blade. This ensures the most torque is created with the least amount of resistance. The angle of attack is crucial. It determines how efficiently the wind's energy is converted into rotational force. But why specifically 3 blades? If we had only 2 blades, the turbine would spin too fast. This overspeeding would create a host of problems, including stability issues and excessive noise. Imagine the constant vibrations and the loud whooshing sound. It would be disruptive to the surrounding environment. On the other hand, if we had 20 blades, the situation would be entirely different. The air flowing through the multitude of blades would become extremely turbulent. The turbine would essentially act like a solid wall, blocking the wind's passage. Very little energy would be extracted, rendering it inefficient. Therefore, 3 blades strike the perfect balance. 3 is the Goldilocks number for wind turbine design. It provides the perfect tip-speed ratio, optimizing energy capture. This ensures the most power is generated while maintaining grid stability. It also contributes to a high capacity factor, maximizing energy output. Now, let's journey inside the top of the tower, into the nacelle. This is where the real magic of energy conversion happens. The spinning blades turn a low-speed shaft connected to a gearbox. The gearbox dramatically increases the rotational speed to thousands of rotations per minute. This high-speed rotation is essential for efficient electricity generation. Inside the generator, we find the core of modern power generation. Rare earth permanent magnets play a crucial role here. These magnets enable direct drive systems, eliminating the need for heavy gearboxes. Direct drive systems improve reliability and reduce maintenance costs. The resulting electrical current is then managed by grid-forming inverters. These are advanced power electronics that do more than just follow the grid. They actively help stabilize the grid's frequency, preventing blackouts. This is especially important during surges in energy transition. Even with our best technology, we face a fundamental limitation. The Betz limit, a law of physics, dictates that no turbine can capture more than 59.3% of the wind's energy. This limit exists because if we extracted all the wind's energy, the air would stop completely. No new air could flow through, halting the energy generation process. To understand this limit, imagine trying to stop a stream of water with a paddle wheel. You can extract some energy, but blocking it completely would be impossible without losing efficiency. The Betz limit is a similar concept. It represents the maximum amount of energy that a turbine can extract from the wind. Despite this limitation, innovation continues to push the boundaries. Today, the revolution is moving towards offshore wind innovations. Massive turbines, the size of skyscrapers, are being deployed in the ocean. These turbines use smart blades to adjust their pitch in real time. This allows them to maximize renewable energy capture, even in the harshest storms. These smart blades use sensors and computer algorithms to constantly adjust their pitch. This adjustment allows them to capture the maximum amount of energy from the wind. The blades also reduce stress on the turbine components. These turbines are often placed offshore, where winds are stronger and more consistent. However, the harsh marine environment presents unique challenges. Saltwater corrosion, extreme weather, and difficult maintenance all add to the complexity. Despite these challenges, offshore wind power is rapidly expanding. It is becoming a major source of clean energy around the world. These advancements not only increase energy production, but also contribute to grid stability. They ensure a reliable supply of power even during periods of high demand. As technology continues to evolve, wind turbines will become even more efficient. They will play an increasingly important role in meeting our energy needs. The future of wind energy is bright. Ongoing research and development promise even greater advancements in the years to come. These advancements will help us harness the power of the wind more effectively. They will also reduce our reliance on fossil fuels. The journey of wind turbine technology is a testament to human ingenuity. It showcases our ability to innovate and adapt in the face of environmental challenges. The wind, once a symbol of nature's untamed power, is now a source of clean, sustainable energy. It is a symbol of our commitment to a greener future. And it is a reminder that with creativity and determination, anything is possible. Engineers work tirelessly to optimize wind turbine design, but other factors also influence their construction. One key element is the airfoil shape of the blades. This shape is carefully calculated to maximize lift and minimize drag, ensuring the turbine captures as much energy as possible. But why 3 blades? 2 blades would spin too fast, causing instability and noise. 20 blades would create turbulence, acting like a solid wall. 3 is the Goldilocks number, providing the perfect tip-speed ratio, capturing energy while maintaining grid stability. The tip-speed ratio is the ratio of the blade tip speed to the wind speed. A higher tip-speed ratio generally means more efficient energy capture, but it also increases noise and stress on the turbine. Inside the nacelle, energy conversion occurs. Spinning blades turn a low-speed shaft, ramped up by a gearbox. The gearbox is a critical component that increases the rotational speed to match the generator's requirements. Inside the generator, rare earth magnets enable direct drive systems, eliminating heavy gearboxes. Direct drive systems are more reliable and require less maintenance. Grid-forming inverters manage the current, stabilizing frequency and preventing blackouts. These inverters are essential for integrating wind power into the grid. Even with this tech, the BETS limit restricts turbines to capturing only 59.3% of the wind's energy. This limit is a fundamental constraint on wind turbine efficiency. To understand this limit, imagine trying to stop a stream of water with a paddle wheel. You can extract some energy, but blocking it completely would be impossible without losing efficiency. The BETS limit is a similar concept. It represents the maximum amount of energy that a turbine can extract from the wind without completely stopping the airflow. Today, offshore wind innovations use smart blades to maximize energy in harsh conditions, mastering the wind. These smart blades are equipped with sensors and actuators. The sensors measure wind speed and direction, while the actuators adjust the blade pitch to optimize energy capture. This allows the turbines to adapt to changing wind conditions. These turbines are often placed offshore, where winds are stronger and more consistent. However, the harsh marine environment presents unique challenges. Saltwater corrosion, extreme weather, and difficult maintenance all add to the complexity. Despite these challenges, offshore wind power is rapidly expanding. It is becoming a major source of clean energy around the world. The development of offshore wind farms requires careful planning and environmental impact assessments. These assessments ensure that the turbines do not harm marine life or disrupt sensitive ecosystems. The construction and operation of wind farms also create jobs and stimulate economic growth. These advancements not only increase energy production, but also contribute to grid stability. They ensure a reliable supply of power even during periods of high demand. As technology continues to evolve, wind turbines will become even more efficient. They will play an increasingly important role in meeting our energy needs. The future of wind energy is bright. Ongoing research and development promise even greater advancements in the years to come. These advancements will help us harness the power of the wind more effectively. They will also reduce our reliance on fossil fuels. The journey of wind turbine technology is a testament to human ingenuity. It showcases our ability to innovate and adapt in the face of environmental challenges. The wind, once a symbol of nature's untamed power, is now a source of clean, sustainable energy. It is a symbol of our commitment to a greener future, and it is a reminder that with creativity and determination, anything is possible. The efficiency of a wind turbine is affected by various factors. These include the wind speed, the blade design, the the generator efficiency, and the grid connection. Wind turbines are typically designed to operate within a specific range of wind speeds. If the wind speed is too low, the turbine will not generate much power. If the wind speed is too high, the turbine may need to be shut down to prevent damage. The blade design is crucial for capturing the wind's energy efficiently. The blades are typically made of lightweight materials such as fiberglass or carbon fiber. The generator converts the mechanical energy of the rotating blades into electrical energy. The efficiency of the generator is a key factor in determining the overall efficiency of the wind turbine. The grid connection allows the electricity generated by the wind turbine to be fed into the power grid. The grid connection must be stable and reliable to ensure a consistent supply of power. Wind turbines are becoming increasingly popular as a source of renewable energy. They offer a clean and sustainable alternative to fossil fuels. Wind turbines can be deployed on land or offshore. Offshore wind farms tend to be more expensive to build and maintain, but they also have access to stronger and more consistent winds. The cost of wind energy has been declining rapidly in recent years. Wind energy is now competitive with fossil fuels in many parts of the world. The deployment of wind turbines is helping to reduce greenhouse gas emissions and combat climate change. Wind energy is a key component of a sustainable energy future. The development of wind turbine technology is an ongoing process. Researchers are constantly working to improve the efficiency and reliability of wind turbines. New materials and designs are being developed to reduce the cost of wind energy and make it more accessible. Wind energy is a promising technology that has the potential to transform the world's energy system. The integration of wind energy into the grid requires careful planning and coordination. The variability of wind power can pose challenges for grid operators. Advanced forecasting techniques are being developed to predict wind power output and manage grid stability. Energy storage technologies can also help to smooth out the variability of wind power. The social and environmental impacts of wind energy must be carefully considered. Wind turbines can have visual impacts and can affect wildlife. Careful site selection and mitigation measures can help to minimize these impacts. Wind energy is a valuable resource that can help to create a more sustainable and equitable world. The future of wind energy is bright, with ongoing innovation and decreasing costs. Wind energy will play an increasingly important role in meeting the world's energy needs. The wind, once a symbol of nature's untamed power, is now a source of clean, sustainable energy. It is a symbol of our commitment to a greener future, and it is a reminder that with creativity and determination, anything is possible. As we build robots to maintain these giant structures, new questions arise. How do these robots actually think and make decisions? To see inside the hardware and the central nervous system of a machine, you have to join us for our next adventure. Inside a robot's brain, how sensors work. I'll see you there, explorers. Engineers continue their work, but other factors also influence their construction. One such factor is the need to minimize environmental impact. Wind farms are often located in remote areas to reduce their visibility and noise pollution. However, this can also increase the cost of connecting them to the grid. The materials used to build wind turbines are also carefully chosen to minimize their environmental footprint. Recycled materials are increasingly being used in wind turbine construction. The decommissioning of wind turbines at the end of their lifespan is another important consideration. Plans are in place to recycle or repurpose the turbine components. The social acceptance of wind energy is also crucial for its continued growth. Public education and engagement can help to address concerns about the visual and noise impacts of wind turbines. Community benefits agreements can also be used to share the economic benefits of wind energy with local communities. Wind energy is a valuable resource that can help to create a more sustainable and equitable world. The future of wind energy is bright, with ongoing innovation and decreasing costs. Wind energy will play an increasingly important role in meeting the world's energy needs. The wind, once a symbol of nature's untamed power, is now a source of clean, sustainable energy. It is a symbol of our commitment to a greener future, and it is a reminder that with creativity and determination, anything is possible. The journey of wind turbine technology continues, driven by innovation and a commitment to sustainability. As we look to the future, wind energy will undoubtedly play a crucial role in powering our world and creating a cleaner, more sustainable future for all.